This video is an introduction into some of the regression analysis modeling that's capable within eSight. Now, regression analysis and performance analysis is purely something that can be done within the advanced features within eSight, so you will need an advanced user account to be able to do this. So in this example, we're going to go through to the advanced section of eSight, and the performance analysis, including regression, specific energy consumption, deviation, etc., are all done within the analysis module. So if we click within performance analysis, in this example I'm going to do, it's going to be looking at gas consumption versus degree days, but equally it could be anything. It could be anything that's got a driving factor, so energy consumption versus number of parts made, number of tons, or whatever it may be. So first thing we're going to do is a specific energy consumption, so kilowatt hours per something graph. Let's look at the gas consumption for a building. So that gets added to the meter. Now the driving factor could be a meter in this case. We've got some good degree day data in here. Just to let you know that within eSight, normally the standard degree day data only is weekly values divided by 7. So for a week, all of the degree days, the weather data is identical. There are identical values. But we can actually get, at Enica, we can get daily degree days streamed in that are more accurate than that. There are individual day values. So for this example, I'm going to take the daily degree days for the Severn Valley. I'm going to add those as the driving force. And now we need to take some period data. So over what period do we want to do this for? And let's say last month. And because we don't have half-hourly degree days, we have daily values. We're going to put that into 1 day values and click Run. Now this gives us a kilowatt hours per degree Celsius, or it could give kilowatt hours per ton or kilowatt hours per part, or however it is we want to do that. The blue line is actually degree days, and the purple bar chart is the sec value. So also we can get the chart data in here. Of more relevance to us, probably for a degree day model and a weather correction model, is regression analysis. So we click the analysis type and change that to regression model. And we keep all of our values the same. Probably want to do it for a bit longer period now. So let's take the previous calendar year, for instance, which is 2017. Again, leaving 1 daily values as the interval. So this is going to draw a scatter graph of the 365 days for 2017. Now on the axis along the bottom we've got weather, so colder up this end of the axis and warmer down in here. And then we've got the energy consumption going up this axis here. And you can see that within eSight we've now got the ability to actually turn on and off different days of the week, which is extremely useful for looking at patterns for certain days of the week. You know, for instance, this one, you can see that all of the Sundays are generally along the bottom of the actual scatter graph, but we have 2 Sundays here that obviously the performance and the gas consumption on this site was abnormal on those 2 particular days. So this is quite a useful feature within eSight for looking at the data in particular. So we'll turn all those back on. And beneath the regression analysis is another very useful chart which shows you the expected consumption versus the actual consumption. So the blue is the actual consumption and the red is the expected. So what we're looking for in here are periods when the blue bars exceed the red, and you can see for this site it happens quite a lot. So we tend to suggest that there's a very limited relationship or very poor relationship between weather driving factor and actual gas consumption. Within the information box, if we click this down at the bottom, we actually get some key statistics about the scatter graph, which are very important. starting off with the R² value. In here, this is actually quite poor data of an R², which is a correlation coefficient of 0.38. This value can range anywhere from 0 all the way up to 1, 0 being there is literally no correlation whatsoever between the two driving factors, the energy consumption and degree days, all the way through up to 1, which would suggest there's a perfectly linear relationship between the two axes. I'd suggest that anything over, say, around 0.8 would be a confident model that there is a good relationship between the two. We have the gradient in here and also the base load, which is the plus C part of any y equals mx plus c scatter graph. So the plus C part would be essentially when there is, in this case, no heating required. This model would tend to suggest that there is still gas consumption for non-weather dependent factors, maybe something like domestic hot water. So one of the next things that we can do is look at the deviation analysis, which is quite similar to regression analysis but presents the data in a slightly different way. Maybe let's do that over period through, let's say, the previous 6 months. And we're going to run that. Again, this is kilowatt hours of gas versus degree days. Now, the 0 point along this axis here is essentially the line of best fit, tilted and flattened out horizontally. So what we can see is anything above this line of best fit, the gas consumption is poorer than we expected for the model. And anything below the line of best fit is the site is performing better than we expected. So what we can see here is probably 1, 2, 3, 4, 5 days of a week, and then the weekends are always performing slightly better than expected in here. Obviously that degree day model at the moment, then the regression model does not discriminate for weekends. So this site is actually, an example is a school, and obviously that school is closed at the weekends. But what this can actually do is give you an idea of the value in kilowatt hours of the poor performance. In other words, performance over what we expected the consumption to be for the weather. And again, in chart data, we can look in there and see that you've got the daily degree days in this column, the actual kilowatt hours, and then the expected values and the difference between the two. There's also a running CUSUM as well. And the next analysis that we can do is some CUSUM analysis. Again, looking at when points in time when things actually change in their performance. And this will run for the last 6 months. So we're looking at big changes. Are things cumulatively getting worse, or are they cumulatively getting better? And directional changes are what we're looking for in this particular model. So directional change around this point in time starts going back upwards, and then there's also a significant change here. So it would tend to suggest that something quite major has happened with those controls. So linked to the deviation analysis in particular is the ability of eSight to flag up an alarm when things move outside of expected conditions. So within eSight, we have this ability to do some deviation range alarming. So firstly, to do that, I'm going to run the deviation analysis and get some values in my mind about where I want these alarms to go. So let's say that we're going to say anything over plus 40,000 along this here, these points in around here, they would be periods when I'm thinking, well, that consumption is way too much for the actual weather. So I want to put some alarms in there. And maybe the negative 40 as well is quite a useful thing to say, well, things are just too good for that. So I'd want to also know about those. So going back onto the actual setup page, I can put some values in here of 40,000 and, sorry, let's put the negative 40,000 as the minimum, the maximum of 40,000, and run that again. And this will draw two lines, essentially, which are thresholds for the deviation analysis. So what we want to do here, in essence, is say, well, okay, when the data, which is the performance data and not the absolute kilowatt hour values, so when the performance is 40,000 kilowatt hours more than expected, then we want to know about that. So that's where we can start putting some alarms in. So what we need to do then is set this as a template and configure it as a template, and we'll call it demo site deviation alarm, and we'll save it in our demo site rather than in the degree days. Save as a new template. Now we've got that saved as an eSight template. So now we can go into the alarms package in alarm configuration, and we can start looking for and setting up some deviation alarms. And these are very specific alarms that work off the deviation analysis. So for instance, we might not want to know when absolute kilowatt hour values go over a set value, because it might be very cold or it might be very warm, for instance. So what we're looking for is deviations in performance rather than deviations in absolute kilowatt hour values. So let's add this alarm. We're going to call it demo site deviation alarm. The alarm language would be English, and the alarm type is going to be a deviation alarm. So the meter that we're going to choose is the gas meter, and the analysis template is the template that we've just set up a minute ago. And let's say that we're going to raise it every 1 day. And this is where we can type in our minimum and maximum thresholds for our deviation. So minus 40,000 kilowatt hours less than expected, and then plus 40,000 kilowatt hours. And these values could be anything that you wanted to select. And we could also have a report that comes with that. So we get an analysis template along with this email. And for instance, we've already set up our template, and we're going to have that as a PDF and as a graph. So if we're just going to click add there, so we need to add a file name for our report in here. So we're going to call it demo site deviation. Right, that's because the template needs a path to live in. So we're going to find our demo site deviation alarm, click add, and click save. So what we've now got is an alarm that's an intelligent alarm based on degree days, based on actual performance away from what we're expecting. So we're saying that if we have a consumption which is the equivalent of 40,000 kilowatt hours more than what we expected for the weather, then we're going to alarm and get to know about that. So this is a very intelligent way of alarms not actually being related to the raw kilowatt hour values or energy values, but more based on driving factors.